We have a guest in the audience who is presenting the colloquium today, and he kindly requested the lecture to be conducted in English. So if this is okay, I'll be speaking English, okay, today. But you can ask questions. If something gets lost, just ask questions and I'll go over it, okay? So let me remind you, so we have covered more or less various things about one-dimensional Ising model. The only thing that I didn't really talk about, it's not central to our development here, but in principle one can consider the point t equals 0 as a critical point for the one-dimensional Ising model. And then one can introduce variables which are not the usual variables. So in higher dimensions, we usually use variables like the deviation from the critical temperature, well, probably this way, right? Scaled by the critical temperature as a scaling variable. And we usually also use some kind of a scaled magnetic field, B over KT or something like this. And so in this particular case, the appropriate scaling variables are not these. So the appropriate thing is something like e to the minus j over kt, or what we called e to the minus beta k. So this is the appropriate scaling variable if you want to define critical indices near this point. So it's possible, but we're not going to do it. So a simple analysis of the expressions that we had. Well, at finite temperature, those things didn't have any singularities, so there was no transition at finite temperatures. But those expressions are singular with respect to these variables near this point. And we can sort of introduce the corresponding critical indices, critical exponents, and see that they satisfy the scaling relations that we introduced. So that's just one comment about what's been done so far. Now we go to the main topic of more or less of the whole course, if you want. We want to study critical phenomena in 2 dimensions. So now we will deal with the Ising model in 2 dimensions. And the plan is to first demonstrate that it does have a transition at finite temperature. Then we will use some duality arguments to find the critical temperature. And finally, we will solve it exactly. So we'll probably not be able to finish the solution today, but we still have some time left. So let's consider Ising model on the 2-dimensional square lattice. There are several comments to be made here already. So for one thing, I have to be rather precise about labeling things now. So the sides of the lattice lying in 2 dimensions will be labeled by 2 integers, right? So we have this, for example, ij, and this will be I plus 1j, and so on. So it will be 2-dimensional two integer indices labeling a particular site. Then it makes sense then to define the bond strengths to be sitting at the centers of these bonds, or on the medial graph of this lattice, if you want. And naturally they would have to be, if we wanted to consider things that are non-uniform, where the bond strengths are different everywhere, we would have to assign some functions kx on the, so kx is the horizontal bond, so it's sitting here, let's say. So it would be naturally associated with this point. So it's integer y index, but half integer x index, right? And correspondingly, we would have ky, which is sitting over here, let's say. So it would be corresponding to I, j plus 1/2. So in general, these guys can be, arbitrary numbers, including positive or negative. So we know that the positive values of k correspond to the tendency of spins to align in the same direction, and negative k's correspond to the tendency to align in the opposite directions. So ferro and anti-ferromagnetic cases. So that's the first comment. So let me, using this notation, let me write the partition function. So the partition function, well, okay. Also, in most cases, I would want to probably, generically, I would like to consider finite lattices with the m sites in the x direction and n sites in the y direction, right? So the partition function then sort of should be, in general, labeled by these two numbers, and will be a function of all the coupling strengths. Okay. So it's going to be the sum over all the spins. Now, from now on, spins will also be denoted by sigma, simply because it's a traditional notation for the using spins. So variables sigma ij take plus or minus 1 values, right? It can be a plus or minus 1. They're sitting at the sides of this lattice. So we sum over all the spins, all the collections of spins. I should sum over all the values of spin ij. And this summation means that they're all independently summed over plus and minus 1. Exponential, and in the exponential I will have summation over I and j. Kx of I plus 1/2 j sigma I j sigma I plus 1 j. That's the first term. That corresponds to horizontal couplings. Well, in principle, I have to continue the exponential here, but let me avoid this by writing it as an exponential, the sum over I and j, ky of ij plus 1/2 sigma ij sigma I j plus 1. So that's the partition function. I'm not introducing any magnetic field here. The reason is essentially because we can't solve the model with the magnetic field. That's an outstanding problem that has not been solved. Okay, one comment on boundary conditions. So in principle, one can consider various boundary conditions here. And in either direction, x or y, it can be open boundary conditions or free boundary conditions where we allow spins to do whatever they want. Or we can, in either direction, wrap the system up in a circle. So it could be free boundary condition everywhere. It could be a cylinder, or it could be a torus, right? And we will probably have to mention this again later. For now, for the next half an hour or so, it won't matter what kind of boundary conditions we're using. Okay, so that's the definition of the model. Also, most of the results, of course, will be presented for the case when all these guys are uniform, except that it's an interesting case is when all the ky's are the same and all kx are the same, but they are different from each other, right? So one can consider an anisotropic variant of the Ising model where the strengths of the coupling in the horizontal direction and the vertical direction are different. Okay, so the first it's a name which is difficult to spell. So in 1936, Rudolf Peierls wrote a paper which was called On the Model of Ising for the Ferromagnetism, where he proved the existence of a critical of a transition in this two-dimensional model for the uniform couplings. It's sort of not quite important for now to make them different. So let's make every coupling the same. So here's the argument. He compared. Remember, we had an argument showing that there is no transition in one dimension. Essentially starting with the ground state where everything was pointing up and seeing how much we would pay in energy by flipping some spins and how much we would gain in entropy by doing that, right? So the same argument can be applied here, and it runs as follows. So again, let's assume that we start with the ground state, which is ferromagnetic. So every spin is aligned in the same direction. And then we want to consider excitations about this ground state. So this is a state with the minimal possible energy. So what are the excitations? The excitations are, of course, some flipped spins. And in principle, we can have a group of spins to be flipped. So if we flip, let's say, these 3 spins, then it's easy to estimate the cost of the energy lost. Namely, we have to draw a line, a polygon surrounding these spins. It's actually a good place to point out that what will be important for us also is the dual lattice to the original lattice. So at the center of each face of this original lattice, we can place a cross, and these crosses form the dual lattice. That's an important object which will be recurrent in the subsequent discussions. So that dashed line goes along the bonds of the dual lattice. Okay? So let's denote the length of this line by L. So this line is called domain wall because it separates 2 domains. One domain where the spins are down and the other domain where the spins are up. Now each segment in this domain wall costs the energy of 2J, because instead of having the spins aligned in the same direction, I should just remind you that what we call K here is proportional to the, for physicists it's somewhat important. So we have, ultimately the projection function is the combination of these ratios, but physically, in physics we vary the temperature while thinking of this J as being fixed. So it's so J has dimension of energy, and that's really the strength of the bond, and T is the temperature. This is a dimensionless coupling constant. So let's look at the energy change when we do this flip here. So the energy change will be positive because we go from the state of the lowest energy to a somewhat excited state, and the energy cost will be 2JL. Because, as I said, every segment of this line costs 2J, because we flip the spins from being aligned in the same direction to being misaligned, and so the relative cost is 2J. At the same time, especially for the long domain walls, there's obviously not a single way of drawing such a line. There are many different ways of drawing a line of length L on a square lattice. And it doesn't really matter whether we precisely write this number or not. This is what we call the omega, right? The number of states. How can we estimate the number of states? This number of states will be, roughly speaking, the following. It's going to be, it will depend on L in this particular case. What I'm planning to say is that this is some positive constant to the power L. So where A is between 4 and 2. So roughly speaking, you can think about this way. So if you draw a line at every site, you can turn left, right, so you can continue in 4 different directions, right? So an overestimate for this number will be the 4 to the L. 4 to the L is just a number of random walks of length L. on this lattice, right, starting at a particular point. So this, of course, overestimates the things because we want to have some polygons which without repeating a particular bond, and also we have to come back to the same place. So this is a good estimate. So, but it's clearly exponential. Okay. Not to mention, of course, that you can place it in many different places on the lattice, right? A particular loop can be shifted. That would only give us some kind of multiplicative number of sites. So that doesn't have to do anything with the length of this loop, right? So that's not important. Okay, so what we call the entropy then, or change in the entropy, is just the k log omega here, and so it's it goes as kl log a. And so finally, the change in the free energy is going to be, as you can see, proportional to L. The whole thing will be proportional to L. It will be 2j minus kt log A. And so now it's clear that depending on what T is, that change is either positive or negative, right? So for low temperatures, this change is positive, which means that the free energy would increase if we flipped the spins. So it's not advantageous to flip the spins. But for high temperatures, high enough temperatures, it will be advantageous to flip the spins to increase the entropy. So that indicates that there exists a critical temperature. From this argument, it's sort of equal to, we can just write it as 2j over k log A. And since this inequality is valid, it's a positive expression. So there's some critical temperature. It's a very simple argument, very elegant, indicating that there is a transition in this system. Okay, so actually the exact value for this thing is known. We will see what it is very soon. Okay. So now let's. So this was really the first paper after the Ising's paper on this model, but after that there was a whole. Again, things were developing gradually. But the next major contribution was done by Kramers and Vanier in 1942. So they wrote a paper where they used the duality argument to find the exact value of the critical temperature. So let's go through this argument. Okay, so this duality observes some formal equivalence of two different ways of representing the partition function for the Ising model. So let's forget about these complications. Let's assume that all the coupling constants in x direction are the same, and all the coupling constants in the y direction are the same. So then let's consider this partition function again and do the following. So it will simplify somewhat, right? So it will be now, I will just, it will be only a function of kx and ky, if you want, right? Two values. And so it's going to be the sum over all the spins, e to the kx sum over ij, blah, 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 e to the ky sum over ij, blah, blah, blah. So we know what these things are. So the basic observation that we will be doing here, we can expand this function at high temperatures as high T expansion. And we have done this for the Ising model, by the way. So the basic observation that we have made that then is that e to the k sigma I j, let's say, let me be precise here. So this guy is oops, oh, I'm using, let me use standard Russian notation for this. So this is where V was, let me, maybe again I will call it Vx. It's the tangent hyperbolic of this guy, right? So that's just a true statement, simply because we could have written it as cosh of this expression plus sinh of this expression. But cosh of this expression being even function doesn't depend on the values of the spins. So it can be pulled out, and then we really get this thing, right? So, and similarly we can do for the y direction. There will be analogous expression for the y direction. And so the whole partition function now looks like this. I will now expand every exponential here in this particular form. And let's see. Okay, let me do, for simplicity, let me do the following, that I want to consider the total number of sites to be, I want to simplify the formula somewhat. Some details are not really essential. So let me assume that there's a notation I'm using is probably bad for this. Okay. So let's count the number of vertical bonds here. So number of vertical bonds with this notation is n minus 1, and let's assume open boundary conditions. I don't really, times m. Number of horizontal bonds is m minus 1n, and number of sites is m times n. Right? So in the thermodynamic limit, when we take both m and n to infinity, these are essentially the same, or at least their ratios go to 1, obviously, right? So the reason I need these numbers is that when I expand, for example, these exponentials, so the number of terms, number of factors in the product will be equal to the number of horizontal bonds. And each of them will spit out a constant factor of that type. So I need to know which power to raise it to. So let's write this partition function then as cosh kx to the power m minus 1n, cosh ky to the power n minus 1m. Right? Then what will happen, there will be still summation over all the spins, and there will be products. Let me call this HB, means horizontal bonds. I will just and I will, again, let me not specify what indices here of sigmas are. It's clear what I mean here, right? Hopefully. And then I'll have a product of vertical bonds of 1 plus Vy sigma sigma. Okay? So what happens now is that we can expand these products, really open all the brackets up. And in either, so each factor here in these products correspond to just one bond. And depending on whether we pick one or this second term, we will not draw or draw this bond on the lattice. Okay? So clearly this expansion will be a collection of some lines or polygonal segments somehow. And then typical term in the expansion will involve some factors of V and some factors of sigma. Factors of sigma, of course, can come up to the fourth power, because we can have configuration which involves just an empty site, or a configuration where a site is entering one line from either direction. There'll be maybe 2 lines, 3 lines, or 4 lines. So there'll be factors or terms in the expansion that contain 0th power of sigma, 1st power of sigma, 2nd power of sigma, and so on. And then when we sum over these sigmas, of course, the odd powers will drop out. They will not be allowed, because we will be summing over plus and minus 1, right? And only these guys will survive. And so if we only allow this kind of local configurations near vertices, the whole thing will be represented as a sum up to this factor over here. So cosh kx to this power. Let me simply call this NV, and this is called NH for simplicity, NH cosh k y NV. So summation will be then over polygons drawn on the lattice, and for each polygon we will have Vx to some power r and Vy to some power s, where essentially r and s will be the number of horizontal and vertical bonds in a given polygon. And by the polygon I don't mean actually a connected polygon. It may be a collection of polygons, right? So each configuration can be several polygons placed in the lattice. That's all I really need to know about this expansion for now. I'm not going to evaluate it in any way. I will just write it this way. Okay? I will just now probably need to write the free energy in the limit. Let me just do the free energy per unit site in the limit. It's really in the limit that the duality will be established. So let's do the free energy as a function of coupling constants, which will be minus T 1 over Mn T limit Mn going to infinity of log of this partition function. Right. T is not that important here really, but okay, since traditionally it has to be here. So let's take the log of that guy. So there will be some factors which will be so the first factor will give you actually let me just remove them right away. So when we take the log of this cosh to the power, this power comes down, but this power in the thermodynamic limit divided by Mn tends to just 1, right? So that's all I wanted to say. So it's really cosh kx plus cosh ky, and then the rest I'll write as let me just call this function something. Let me call this capital phi of Vx and Vy. That's a definition of this function, if you want. So it's a log of that summation over polygons divided by the number of sides in the limit. Thank you. In fact, I need more than that because, sorry, well, the factor of 2, which is missing here, summation over spins. Well, so there's an overall factor of 2 to the mn here, because each summation over spin gives you a factor of 2, actually, right? So, but that's just a constant. Log 2 or something, right? So this is not really that important right now. It could be included over here. It doesn't really matter. Okay, so that's a formal representation of the free energy in terms of some function that has an interpretation in terms of some series over the polygons. Now let's do the low temperature expansion. There's an alternative way of doing representation of this partition function, which is based on a totally different point of view. So in high temperature expansion, what we rely upon is that these values, Vx and Vy, being hyperbolic tangents of some positive numbers, are less than 1. So these are sort of natural expansion parameters. We can hope that this series is convergent, let's say, for some ranges of temperature. So, well, in anticipation, we of course know that this series does converge for T greater than Tc, and it blows up at T equals Tc, or it has some problems with the convergence at the critical temperature. Okay, now let's now try to start, instead of coming from the high temperature side, let's try to go to the critical point from the low temperature side. And at low temperatures, the basic picture is again that we have this predominantly aligned spins with sometimes flipped islands of spins or domains. And so the typical configuration in the low temperature side looks like an island, sort of islands of overturned spins in the sea of. So it's exactly the same picture that we had for the Peierls argument. So each configuration that we have to sum over on the low temperature side will look like this, right? So, and the statement then is that every polygon drawn on a dual lattice will now will cost a certain energy that we know. We have already written this energy. Now, well, let me just be slightly more specific. Suppose R is the number of, let's see, horizontal links on a domain, on the domain wall. And S will be the number of vertical ones. And it may not be a single domain wall. It can be a collection of domain walls, right? Then this state, relative to the ground state energy, will have so the contribution to the partition function of this thing will be, relative contribution to the partition function will be e to the minus 2kx r e to the minus 2kx 2kys. Right? So the partition function itself will then be simply let me write what it is. Factor of 2 I'll explain in a second. So let's see. So I will just have to now count all the bonds. So we agreed that there would be NH bonds that are horizontal, and there will be NV bonds that are vertical, and then there will be a sum over the polygons on the dual lattice of this type. That's the partition function. Okay, maybe I should just say how this is done. You really count how many broken bonds you have and how many unbroken bonds you have, and you can really tell what the total energy is for each configuration. You just exponentiate it, and that's what it is, right? Every unbroken bond contributes just e to the kx, and you just count them. But relative to this state, so this is the contribution of the totally aligned state. And every time you flip a bond or flip a spin, the corresponding bond will give you a contribution of e to the minus 2kx. So that's what's written over here. Okay? Questions? Okay. So now we can write this thing as well, the free energy can also be written, of course, for this thing. And notice that, oh yes, factor of 2 comes from the point that in the low temperature picture, every configuration is doubled, because we can have all the spins pointing up or all the spins pointing down. And for every drawn domain wall, we can still flip all the spins and get the configuration of the same energy. So this is where this doubling comes from. Okay, now let's take the free energy again as a limit, right? And the interesting thing to notice is that if you have, especially in the periodic case with the system on a torus, or simply in thinking about how in the limit, the boundary does not really matter, this is the sum of the same type as appeared over there. It's really the sum of the same type of polygons on the same type of lattice. The lattice dual to the square lattice is still a square lattice. So it's the same sum, except that the arguments are different, right? So the free energy then can be written as minus t. When we take the log here, we'll get just kx and ky. Sorry, here, right? And then we'll get the same function phi that was defined over there, except that it will be now written as a function of e to the minus 2kx, e to the minus 2ky. Okay? So we now have a representation of, and the same log 2 appears actually. So it's the same constant here, that is log 2. Up to, well, so maybe it's inside, well, maybe I should write it here, inside the brackets here, log 2. Okay.
Why do you put it inside brackets?
Is it? Oh, it disappears, right? You're right. Yeah, it's just not there. You're right, absolutely. Thank you. In the limit, it just disappears. Yeah. Oops. Okay, so the statement now is that we have two different expressions for the free energy that seem to be valid on different sides of the transition, right? And so one has to then say, okay, so let's now introduce a special dual variables. Let's call them kx star, which is, and ky star. Notice that duality somehow interchanges vertical and horizontal links. Whenever we have a horizontal bond of spins, right, and we care about whether they are aligned or not, the corresponding dual lattice link will be a vertical link, and vice versa, right? So the duality then sort of interchanges x and y, and the rule is that the tangent hyperbolic of k star x is the same as e to the minus twice ky, and tangent hyperbolic of ky star is e to the minus 2kx. So this is just a formal notation. In fact, this is, well, there are many consequences of these things, but one of them, you can easily convince yourself that this is a mutually dual transformation. So if you want to express ky in terms of kx star, it will be the same formula. You can erase star here and put it there. It will be the same. It will be a valid formula. So it's a, okay, and it also can be written in a slightly more symmetric way. So for example, you can write sinh hyperbolic of twice k star x times sinh hyperbolic sinh of twice ky equals 1. Okay? And correspondingly for the just the consequence of this definition. Oops. Okay, so then the statement about the free energy then can be, if you so this naturally can be called what we call Vx. Let's call this Vx star, because it's a tangent of kx star. And here we had Vx, which was the tangent of the original coupling. And this guy we naturally call Vy star. So we see that the free energy in different regimes can be expressed to the same function phi of two different variables. Now let's this transformation, this is called the duality transformation, relates the low temperature phase of the model with the high temperature phase of the model. Indeed, if we consider, let's say, these guys to be large, that's the low temperature phase, the corresponding kx stars will be small, which is the high temperature phase, and vice versa, right? Then the free energy expressed in terms of new couplings, let's say, which is depending on what we start with, is high or low temperature phase, can be related to the free energy of the original model of the original couplings in the opposite phase plus some log sinh 2kx sinh 2ky. And so the statement is then that essentially the two phases are related. We can express free energy in one phase in terms of the free energy in the other phase. Now assume that there is a critical point somewhere. So this function would have to have a singularity at some particular temperature. Then this relation would tell you immediately that this function will also have some singularity. It's the corresponding dual temperature. Okay? That alone tells you that the singularities of free energy must come in somehow in pairs. Right? There will be if you have some singular point in the high temperature phase, there will be also a singular point in the low temperature phase. But we don't expect this to happen. We only expect to have one particular singular point. That means that these two guys are actually the same. The singularities appear at such values of couplings that they're equal to each other. Okay, so let's express it first. So consider first an isotropic situation. Just one single coupling constant K. So then the free energy, then the geology transformation really exchanges K and K star. Right? And in this situation, there's just one parameter, the temperature, nothing else, right? And we say that if we have some singularity at the value of K in the function f, there's also singularity at the value of K star of this function. So there are two different singular points which we don't expect. So essentially this should coincide. So this argument tells you that the critical point Tc is determined by the condition that K star is equal to K. Okay? And since in this isotropic situation, this duality transformation can be written in terms of the sinches, that follows that sinh 2k critical is equal to 1. And that gives you the precise value of the critical temperature. So you can solve it essentially for, let's see, I probably have a, just a sec, let me get the value from here. Oh, well, it's given, well, I mean, okay. 2, 2, 6, whatever, 9, J. KGC. Well, it can be actually solved explicitly in terms of some log of square root 2 or whatever. I mean, it's a quadratic equation in terms of the exponential of Kc, obviously, right? So we can solve it. Anyway, so this is the first determination of the exact position of the critical point in this model. By the way, I should say one thing that is of general comment, general character, is the following. So we talked about universality behavior, universal behavior at critical points. And I may not have stressed enough that some aspects of these critical behaviors are universal indeed, and some of them are not universal. So in this case, we have determined the position of the critical point, which is by no means universal. So you change the lattice, there'll be a different temperature corresponding to a critical point. So the position of the critical point is not universal, and it's just a lucky coincidence, lucky fact that we can find it here in this case exactly. But critical behavior near this critical point will be universal. So all the exponents and stuff will be the same for all Ising models on all lattices in 2 dimensions. Okay, but before we proceed further, before we actually have a break, let me just have one more comment. So let's come back to the anisotropic situation. So the anisotropic situation does the following. So it, if we combine these 2 equations, what we can write is the following: the product of sinh of the dual variables in the x and y direction is equal to the inverse of the product of the sinh of the original variables, right? We just multiply these 2 things together, and this is what we get. And the transformation between the dual and original variables can be now interpreted geometrically as we can draw the diagram in the kx, ky plane, where this transformation has a fixed line now, right? The fixed line, which looks like this, simply corresponds to this product being equal to 1, because this is where it's fixed. Right? That specifies a line in this phase diagram. That's the fixed line of this duality transformation. And so we expect, on the same grounds, that the high temperature phase and low temperature phase being related by this duality transformation are separated by a critical line. So in the anisotropic case, we have still, for every kx and ky, we are either in the low and high temperature phase, but we can now find a line in this space which corresponds to critical behavior. Let me now make one comment about how this can be extended to other types of lattices. So that's very interesting. So the Ising model can be defined on any types of lattices. And for example, we can define it on a honeycomb lattice. And if you, again, this can be done carefully and in detail. I'm not going to do it. But it's clear that if you now think about what the corresponding dual lattice is, it's going to be a triangular lattice, right? So if you place crosses in the centers of the faces of the original lattice, there'll be a triangular lattice. And so by repeating the argument that has been just presented, you could relate the low temperature phase, let's say, of the Ising model on a honeycomb lattice to the high temperature phase of the Ising model on a triangular lattice. So that alone does not really help you, because you sort of can't, you go from one system to another system. That will not tell you anything about the critical point in either of them, right? So, but definitely there's a duality between the Ising model on the honeycomb and the Ising model on the triangular lattices. But in addition, there's one trick that allows you to finally reduce problem of one lattice to the problem on the same lattice but in different phases. So and the trick is called star triangle equality, and it is based on the fact that the honeycomb lattice is bipartite. So it consists of sides of 2 different types. So let me draw them like this, right? So such that the sides of one type, let's say A type, only neighbor with sides of the opposite type. And then what you can do, you can take the Boltzmann weight or Gibbs weight corresponding to these 4 spins, single out this guy, and actually sum over it. Because this spin does not appear anywhere else in any partition function. It will only appear coupled to these guys. So the corresponding expression can be just summed explicitly over this particular spin. Okay? You'll get something. And interestingly enough, that something can be written now in terms of the spins which are sitting just here. And the resulting expression may be written as the Gibbs weight of the Ising model on the triangular lattice of the shaded sites. Okay? So that star triangle transformation combined with the duality allows you to find the exact critical temperatures for the triangular lattice and for the honeycomb lattice. And they all are different from they're both different from the square lattice. And it's clear, so the tendency is that if you have more neighboring sites, then you need to have higher temperature to disturb the system enough to become disordered, right? If you have many neighbors that align you, help you to align in a particular direction, you need higher temperature to break this tendency. So out of all these lattices, the triangular lattice has highest number of coordination number for each site. So it has highest critical temperature, and it can be exactly found using these ideas. Again, this is something that I'm not going to, since we are not, so the main point here is that these tricks can be played not only for the Ising model, for other models as well. But typically, you get something that is not very universal this way, right? As I said, the temperature, critical temperature in these three different models is different. Nevertheless, the critical behavior is the same. Okay, so one more thing to be said about duality is the following: that we, as usual in the Ising model, we are not only interested in the free energy or partition function, but also in the correlation functions. So the natural objects to consider are spin correlation functions, right? This kind of stuff. And there is a duality extended to the level of correlation function that I do want to spend some time on. So the natural variable that is dual to the spin variable exists in the Ising model, but it cannot be formulated in a local way. It's a rather strange object called disorder variable. And it's a case of a variable that is defined through its correlation functions rather than by itself. So let's again draw this square lattice and its dual lattice. So let me put the crosses at the centers of the faces of the original lattice. These are the vertices of the dual lattice. So the claim is that this new variable, the disorder variable, will live actually on the sides of the dual lattice. And for every given site R, let's call it R. So R vector is just ij. It's a two-dimensional vector. The corresponding R star will be, this is just my choice. It's an arbitrary choice. I will introduce corresponding dual site, which is just shifted by 1/2 lattice spacing in both directions. That's where I will place my disorder variables. Okay. Now let me consider a formal object. I will explain what this is. I will introduce it first. So I first have to choose 2 points on the dual lattice. So this will be, let's say, R1 star. And this will be R2 star. Okay. And now I want to do the following. I want to draw a path on the dual lattice between these two guys. Maybe I'll use color chalk here. Some path. Okay? What I do next, every time I cross a bond, I will flip its sign. So I now go to a set of bonds that are different. Okay. So these are bonds of the original lattice, right? So I flip the sign of these bonds. So that introduces some kind of a frustration in the system, disclination or dislocation, right? Because normally the spins here in the original formulation want to point in the same direction. Now, once I flip this sign, they want to point in the opposite directions. Okay? So, given this modified set of bonds, I can still find the partition function formally, just sum over all the spins. So let me call this partition function z of k prime. Then I divide it by the original partition function, and this ratio is called the correlation function of these disorder variables. That's the definition. Now one has to be careful about whether this definition makes sense even, right? For example, one has to convince oneself that this does not depend on the path chosen between the two sites. And that's rather easy to see that it does not. Simply because well, I'm talking about the uniform Ising model here. So that's somewhat important. If one deforms a path on the dual lattice to a different path between the same two sites, that will define an island of spins. And one can convince oneself that if one flips the spins inside the island, you will get essentially to the corresponding configuration. Well, this is the way to prove that since both partition functions contain the states with flipped spins, this is the way to see that this correlation function does not depend on the paths on the dual lattice.
Is it also true for periodic boundary conditions?
Well, no. So of course this is tricky. Periodic boundary conditions, either direction will introduce non-trivial cycles, and that's So let's avoid this for now. I mean, I don't want to do this right now. It's kind of makes it more complicated. Well, one can actually do a similar thing for a single disorder variable. In this case, one has to do the following. One has to take a site on a dual lattice and draw a path to infinity, okay, on the dual lattice, and change all the bonds which cross this path to minus k's. You can still find the partition function. In this case, what you get is will be just an expectation value of one disorder variable. Okay. So intrinsically, this guy is not local because it requires, in the original terms, introduction of some kind of strings, or for this single guy, it's an infinite string that goes to infinity, and you have to change infinitely many bond strengths to even define this guy, right? So the duality transformation then can be seen in the following way. If you remember what the duality transformation was, it was something like this, right? Well, alternatively, I can write it 10k is e to the minus 2k star. So if we flip the sign of k, then you can see that you cannot have now a solution in terms of a real number here. So if k is negative, then k star must be complex. So this, when k goes to minus k, k star actually goes to k star plus I pi by 2. Okay, So that's just a formal observation. But motivated by this, I can actually do the following. I can actually, so in terms of the original formulation of the Ising model, this correlation function is no big deal. We just insert this product of spins in the in front of the weight and sum over the configurations. But one can formulate the spin correlation functions in a completely analogous way to these guys. Namely, one can do the following now. One can do the shift in the original bonds in exactly the same manner. So you can draw the original lattice, no dual lattice involved. Take two spins, and now draw a path on the original lattice between these spins. Doesn't matter which path again. And modified bonds. So, and the rule is that the original bonds are shifted by I pi by 2 on the blue bonds. Okay. Now notice what happens with the Boltzmann, with the Gibbs or Boltzmann factor. So you have two spins, neighboring spins here, right? This guy becomes e to the k prime sigma sigma, and this is e to the k sigma sigma times e to the I pi by 2 sigma sigma. Well, and it's an interesting fact that no matter what this product is, it's either +1 or -1, right? Exponentiating it with this factor gives you plus or minus I. So this thing is equal to I sigma sigma e to the k sigma sigma, right? And so just modifying this weight, this bond strength, brings down the product of two spins in front of it, the usual Boltzmann weight, right? So then you can sort of do it along this path, and every time you pull down this product, so the spins in the interior of this line will square to 1, and the only things that will be left untouched are the original and final spins. So that proves that if this is R1 and this is R2, that sigma R1, sigma R2 is minus I to the n z of k prime divided by z of k. Okay? Where n is the length of this path. So these formulations are very similar. So in this case, we draw the path between disorder variables on the dual lattice. In this way, we draw a path between spin variables on the original lattice. And a little thought can actually be, is required to realize that these two things are related by the duality transformation. Because whenever we change the sign of this bond, we add I pi to the corresponding dual bond, and vice versa. Right? So that tells you that the disorder variables, correlation function of disorder variables in the high temperature phase is the same as the spin correlation function in the low temperature phase, and vice versa. So this duality can be extended to correlation functions, but you need to introduce new variables. Well, for example, I mean, just one simple fact that is easy to see. Let's imagine what happens at infinite temperature. At infinite temperature, the spins are completely uncorrelated. I mean, the average of the spin is equal to 0, right? The average magnetization is equal to 0, and correlation function of any spins is equal to 0 because they're completely independently flipping. So when t is infinity, k is actually 0. So when you flip k to minus k, you don't do anything, really. So at infinite temperature, these two things are the same. And therefore, the disorder variables are totally correlated. At infinite temperature, mu and mu at every point is correlated, right? And the spins are uncorrelated. So it's exactly the dual description. And you can, but more general relation is that when you go to the dual temperature, then the spin correlation functions go to disorder correlation functions. Okay, and one final comment, which actually we'll come back to again at some point, is that one can consider correlation functions of both types, right? One can insert more than 2 disorder variables and more than 2 spin variables in the same correlation function. Multi-point correlation function, which will be defined by a collection of paths. You'll have to break. So, for example, a correlation function of 4 such objects would require you to introduce 2 different paths. You break them into pairs, and you draw paths between the pairs, right? Between members of each pair. Again, one has to be careful. Well, one has to convince oneself that this is a consistent procedure, that it doesn't depend on how you break them into pairs and so on. But you can also combine these guys with the spins and draw the paths on the dual lattice and on the original lattice and see how this interact. And then you will realize that something strange is happening. Because in that case, whenever you cross the paths on the dual lattice and the original lattice involved in the definitions cross, you have some kind of a minus sign appearing in this business. So that means that the correlation function, which are mutual correlation functions of mu's and sigmas, actually depend on how you choose the paths. So it makes them kind of weird. They're not natural correlation functions. Nevertheless, if you stick to a particular choice of paths, then you can see how it will change if you take one of the constituents of your correlation function and drag it around another one and come back to the same point. That will, so suppose you had some correlation function that didn't have any crossings of the paths, and you do this procedure, you drag one of the spins around the disorder variable, let's say. That it will necessarily introduce a crossing or entanglement, if you want, and you will see that the correlation function will change sign. So the sigma and mu variables are non-local, mutually non-local. So it's sort of somehow they know about the not the mutual position, but somehow the prehistory, if you want. So if you fix particular choice of the original path, and then you drag one thing around the other, you'll see a change in sign. I'm not going to dwell on this, but I want to mention one more thing about this, which is related. One can naturally, so this is getting to the heart of the things that many people here are trying to do. So one can formally introduce a combination of a spin sitting at a site and the mu variable sitting at the nearest corresponding dual site, right? The way I defined, let's say here. So if I want to define a single object, sigma r, mu r star, I can always think about these pairs only, right? And once I have only one mu, I have to choose a particular string. Let's say I always choose the string that goes to the left. One choice. So this object has a special name. It's called psi, and it's also called a fermion. That's a fermion in the Ising model. And that fermion has a strange property. Again, it's a non-local object, which if you have two fermions and you drag them around each other, you will flip a sign, simply because the strings will get entangled. Okay? Now, how these fermions appear and how they lead to some sensible critical theory is a subject of some future lecture. It's not going to happen today. So, but this is a very important object. This is essentially the Smirnov observable. That if you're familiar with this object, that's precisely what it is. Okay. So it's called in mathematics it's called Smirnov observable, but essentially these guys appeared as early as 1949, more or less, in the works of Kaufmann, who was a student of von Sager, who solved this Ising model. Okay, we'll come back to them. They'll reappear. But okay, so now I have to switch gears. So this is all about duality. So I'm not going to talk about duality anymore. More can be said about it, but this is enough for today. What I want to do now, I want to start. We don't have much time, but let me at least set up a few things for the exact solution of the Ising model using some other kinds of fermions. All these fermions are related, of course, but not. The relation is not very direct. So, in particular, fermions that appear here are objects that live in 2 dimensions. The fermions that I'm going to use to solve the Ising model exactly will live in 1 dimension. So that's somewhat different. Okay, so there are many different exact solutions indeed, and so some books have wrong solutions. For some strange reasons they give right answer, but there are many wrong solutions. Not many, but at least one of them. In Landau and Lifshitz, there's a wrong solution using the Ising model. And in the latest edition, they actually acknowledge that there's a mistake in the derivation that was somehow corrected, but still. So they didn't change the solution. So I'm going to give you one solution which is not wrong, but which is, in my mind, very elegant. So it's my favorite solution. That's why I'm showing it to you. So let's again write the partition function. And now I'm going to be slightly more specific. So I want to write a summation of all the spins. And in this case, I indeed will consider a problem of on a lattice with m horizontal sides and n vertical sides. So so I want to write it this way. So it's going to be summation of maybe, let's see. Right, that's right. So summation over little n from 1 to capital N, kx sum over m from 1 to capital M, sigma n m, sigma n plus 1 m. So that's the horizontal bond. I add the vertical bond. And in this case, I actually increase the m index, right? Okay. So this double sum could be pulled out, but it doesn't really matter. So this is the thing. What I want to do now, I want to write it as a product of many factors here, still summed over all the spins. Let me call it this way. So it's going to be T. So there will be some object that will appear here, T, that will have a set of indices labeled by. So I should now imagine the following. So I take the first row of these spins that corresponds to m equals 1. See which? Sorry, just a second. Yeah, I want to try to. Let's see which way. Yeah. So the separation of these summations was chosen because of the following: that n will be labeling vertical rows actually, right? So it's n equals 1 here. Horizontal rows will be labeled by n. This is n equals 2, and we go up to n equals capital N at some point, right? And the factors here for each given n, for each n, let's say n equals 1, only depend on the spins sitting in the nearest neighbor's rows, in the first row and second row, for example. And we can view this object in the usual brackets as a matrix element of some big matrix that takes values of the spins over here, multiply, and so it acts in a space that is labeled by the values of the spins here. So if we have m spins total here in this horizontal row, then the number of states of on this row will be 2 to the m. So these states will be labeled by all the spins here, and then we have next row where we also have 2 to the m possible values of spins, and for each configuration of spins in the second row and the first row, there's a corresponding cost in the energy or in Boltzmann weight. That number will be called the matrix element of the transfer matrix. Okay, that is labeled by all the states here and all the states here. So it's a 2 to the m by 2 to the m matrix. It's a huge matrix, right? So let me, having this fact, I mean, I have to use multiple indices to label this matrix. So for example, the first element here will be simply labeled by, let's say, sigma 1, 1, sigma 1, 2, that's right, sigma 1, m, and it goes to sigma 2, 1, sigma 2, 2, sigma 2m. So that's the value of this guy, of this exponent for n equals 1. So let me write it down. Then the next guy will give you transformation from the second row to the third row. So on. And the last one in this thing will be connecting the n minus 1 row to the nth row. Okay, let me write this matrix element so that it becomes clear what I really mean here. So it's just an exact rewriting with an interpretation, right? So there's no trick involved here. I just so t sigma 1 1 sigma 1 2 sigma 1 m sigma 2 1 sigma 2 2 sigma 2 m is simply exponential of k1 kx sum over m sigma 1 m sigma 2m, right? Plus ky sum over m sigma 1 m sigma 1 m plus 1. Well, I have to be careful about the upper limits here, actually. So, I would like to have some kind of a trace structure in this matrix product. So to do this, I have to impose some periodic boundary conditions. In fact, I want to impose periodic boundary conditions in all directions. I want to impose them in the x and y direction. So these will imply that sigma, let's say, n plus 1 m that's in the vertical direction, is the same as sigma 1m. So we just close this thing in the vertical direction on itself, and in the horizontal direction as well. Okay. So the second one is not important for what I'm going to say, but this one, the condition that in the vertical direction we go to the same sites after repeating n steps, tells us that this summation can be written as a trace of this matrix raised to the power n. So the partition function of this system happens to be the trace of the transfer matrix raised to the power of the number of horizontal rows. Okay? So that's completely analogous.
You should write sigma n m is equal to sigma 1.
What?
I mean, in periodical order conditions, probably you should delete n plus 1 or...
No, I want to have n distinct rows, and after n steps you
Yeah, but then you should multiply by the next term on the left.
here?
No, I mean down.
Yeah, you're probably right. Yes, you're probably right. So let's see. Yes, you're right. So let's, okay. N plus 1, 1, n plus 1, m. Thank you. This here, it's also sum up to m, correct. So these are subtleties that unfortunately do matter. Again, they don't matter for critical behavior and the continuum limit and the thermodynamic limit, but technically one has to be careful here. Okay, so it's a trace of some matrix, some huge matrix. And the idea of this whole method of transfer matrices is that if one could diagonalize this transfer matrix, then the trace would be simply given by the sum of the powers of the eigenvalues. And that would be very easy to, well, in principle, to control. In particular, if there were a gap in the spectrum of the eigenvalues, then only the highest eigenvalue would be contributing to the thermodynamic limit free energy, right? So if this is a sum over eigenvalues, the nth power, and there's the highest of them, the biggest eigenvalue, then taking the log of this guy will obviously, and dividing it by n, will, of course, the only one of them will survive. So only the highest eigenvalue will contribute to will determine the free energy in the thermodynamic limit. So that's the idea. But to achieve this, we would have to be able to diagonalize this transfer matrix. And this is not an easy task, but it's doable. So we can do it. Probably it does make sense to do it now, but let's do it next time.